LNG and its low-GHG alternatives, biomethane and e-methane, offer a promising pathway for both short-term and long-term emissions reductions. However, while LNG-capable vessels and bunkering infrastructure are expanding quickly, the scaling of biomethane and e-methane is constrained by upstream fuel production. LNG has been a well-established marine fuel for several decades. Today, there are more than 800 LNG-capable ships operating worldwide, and more than 600 in the order book, and that's not even counting LNG carriers. LNG can improve air quality and can lower a ship's GHG emissions, but it is still a fossil fuel with notable well-to-wake emissions. Even so, it offers a pathway towards liquefied biomethane and e-methane, fuels which can be carbon neutral when produced from sustainable sources. Biomethane and e-methane offer a strong route towards net zero emissions for LNG-capable ships, since they can be burned on board without technical modifications. Both fuels can leverage existing natural gas infrastructure, using distribution pipelines when gaseous, and LNG bunkering facilities and onshore storage tanks when liquefied. Both fuels can be produced with very low GHG emissions, e-methane from renewable electricity and sustainable CO2, and biomethane from sustainable biomass. When sourced from manure, biomethane can even deliver negative GHG intensity by preventing methane from escaping into the atmosphere.
Several key challenges must be addressed before maritime use of biomethane and e-methane can scale. A critical aspect is cost competitiveness. Both fuels currently have significantly higher production costs compared to fossil alternatives, with liquefied biomethane recently trading at roughly 3 times the price of fossil LNG in Rotterdam. However, when factoring in reduced compliance costs under FuelEU Maritime and the EU ETS, along with potential revenue from selling surplus allowances, a business case may exist for some vessels, though this remains largely confined to vessels operating within Europe. Supply is another challenge. Global biomethane production is about 7 million tons per year, nearly double its 2020 level, and this could grow to 50 million tons already by 2030. E-methane production, on the other hand, remains limited today, though it could reach about 1 million tons annually by 2030 if production projects in the pipeline materialize. Although these are significant volumes, they must serve multiple sectors beyond shipping, such as heavy-duty transport and power generation. In the end, shipping's willingness to pay relative to other sectors will largely influence available volumes. Infrastructure integration can make a big difference on availability for shipping. Existing LNG bunkering and natural gas pipeline networks can handle biomethane and e-methane without technical adjustments, serving to reduce transport and infrastructure development costs, encouraging further investments. But to fully benefit from this compatibility, low greenhouse gas methane must be allowed to mix with fossil natural gas in the fuel distribution chain. This can only be enabled by a flexible chain of custody model, such as mass balance, which allow for tracing greenhouse gas emissions in the supply chain without necessarily physically separating fuel molecules of fossil origin and renewable origin. While the EU permits mass balancing within the EU ETS and FuelEU Maritime regulations, global alignment remains uncertain, as chain of custody rules under the IMO Net Zero framework are still under discussion.
Although use of low GHG methane in the world fleet is still limited, we noted a strong growth the last year. For example, Hapag-Lloyd will bunker 20,000 tons of biomethane in 2025 and 2026. The bio-LNG will be bunkered on board the growing fleet of LNG-capable vessels in Hapag-Lloyd's fleet. This supply has been secured through a tender with the Zero Emissions Maritime Buyers Alliance, marking one of the largest commitments to low-carbon fuels in container shipping to date. Biomethane and e-methane offer promising pathways for LNG-capable vessels to achieve future net zero emissions. By building on today's mature infrastructure, these fuels can play a significant role in maritime decarbonisation. Ammonia is another alternative fuel with the potential to transform the maritime industry. However, it also brings some unique safety and handling challenges that must be addressed. Ammonia is a hydrogen-based, carbon-free fuel that is easier to store and transport than pure hydrogen, with a liquid volumetric energy density that is 50% higher. It releases no CO2 emissions when used on board, with decades of experience handling ammonia in the gas carrier segment and a well-established global supply chain. The industry is well positioned to scale its use. This foundation will be essential as the industry shifts from today's brown ammonia to low and zero carbon blue and green alternatives.
While ammonia faces similar supply and cost challenges as other alternative fuels, it also has some unique safety and handling challenges that must be carefully managed. Ammonia is toxic to humans, so exposure must always be maintained within safe limits to safeguard people on board or those in proximity to the vessel. Therefore, technical safety measures should be integrated into ship design as well as operational procedures with the aim of minimizing and controlling ammonia releases. This includes implementing systems to prevent operational releases of ammonia, strict bunkering procedures based on thorough risk assessments, providing safe havens for people on board where they can seek refuge, and ensuring clear evacuation plans in the event of accidental release. In addition, suitable protective equipment must be available, and crew and onshore personnel must be thoroughly trained and familiar with ammonia-specific hazards to ensure safe operations. The industry is working closely with regulators to develop new safety standards and adapt existing technologies to ensure that ammonia can be used safely as a marine fuel. With high levels of industry-wide collaboration and innovation in recent years, notable developments have been made to overcome these barriers, with significant progress around the technical maturity of engine technology and systems. There has also been a lot of movement on the regulatory side. In the IMO, a first version of interim guidelines for the safety of ships using ammonia as fuel was finalized and approved in 2024. Interim guidelines for utilizing ammonia cargo as fuel under the IGC code were finalized in 2025 and are scheduled for approval in May 2026. The first use of ammonia has been demonstrated by a supply vessel and a tug. More than 40 ammonia-capable vessels are on order, with several deliveries expected in 2026, marking a major step toward an ammonia-powered fleet. Further progress is still needed, but developments in recent years have demonstrated how sharing best practices and learning from early adopters is essential to building confidence in ammonia as a safe marine fuel.
One of the most significant milestones in ammonia-fueled shipping is the Yara Eid, the world's first ammonia-powered container vessel. Developed by Yara and its partners, this groundbreaking ship leverages deep expertise in both maritime operations and ammonia handling to safely transport cargo using ammonia as its primary fuel. With safety at the core of its design and operation, the Yara Eide is demonstrating how the industry can overcome the unique challenges of adopting this zero-carbon fuel at scale.
Alongside ammonia, hydrogen is also emerging as a promising zero-carbon fuel for shipping. Like ammonia, hydrogen, which serves as a foundation for ammonia, can be produced using renewable energy and offers the potential for completely emission-free operations. However, several key barriers still limit its uptake. Hydrogen remains costly and its technologies need maturation in the maritime environment. Storage is a key challenge. Because of its low volumetric energy density, storing sufficient volumes on board is difficult, especially for deep-sea vessels. Safety is another concern, as hydrogen is highly flammable and must be stored at extremely low temperatures in its liquefied form. Despite these challenges, progress is being made. Demonstration projects and technological advances are paving the way for hydrogen to play a significant role in the maritime energy transition as part of a broader portfolio of alternative fuels.
By working together, the industry can unlock their potential of these hydrogen-based fuels while still ensuring the safety of people and the environment. Methanol offers another potential pathway to net zero. It benefits from a growing methanol-capable fleet and established supply chains, but low GHG alternatives such as biomethanol and e-methanol remain much more expensive than conventional fuels, and supply is struggling to scale. Methanol is a sulfur-free fuel that burns cleanly, with very low NOx emissions and almost no soot or particulate matter. Tank to wake, it emits about 7% less CO2 than heavy fuel oil, but fossil-derived methanol typically has higher well-to-wake GHG intensity. For real decarbonisation, the potential lies in biomethanol and e-methanol, which both offer near-zero life cycle emissions. This is being supported by established safety standards and growing industry adoption. One of methanol's biggest advantages is its simplicity. As a liquid at ambient conditions, it's far easier and safer to handle than gaseous fuels like LNG, ammonia, or hydrogen. The technology is also mature. Over 100 methanol-capable vessels are in operation, with over 300 on order. Two-stroke engines have accumulated more than 600,000 operating hours, and four-stroke solutions are now entering the market. Methanol also benefits from strong existing infrastructure, with established supply chains and storage at over 115 ports, providing a strong foundation for future scaling.
We see that some key challenges must be addressed before methanol can fulfill its promise as a decarbonization option in shipping. The biggest challenges are cost and supply. Fossil methanol is widely available, but its well-to-wake greenhouse gas footprint is poor. On the other hand, low GHG methanol, such as biomethanol and e-methanol, come at a significantly higher price point, and current supply is limited. The cost challenge is particularly acute for carbon-based electrofuels like e-methanol. Its production requires large amounts of renewable electricity to generate green hydrogen through electrolysis, which is then combined with captured CO2 to synthesize methanol. This process is energy-intensive and capital-heavy, making e-methanol several times more expensive than MGO. Scaling production will depend on massive investments in renewable power and carbon capture infrastructure, both of which are still developing. Biomethanol faces its own constraints. While it can be produced from sustainable biomass, feedstock availability is limited and often competes with other sectors like agriculture and bioenergy. Logistics and processing costs add further complexity, while its cost is also significantly higher than conventional fuels. Scaling methanol use will require strong, sustained demand to unlock production capacity. Even though the global fleet includes a growing number of methanol-capable vessels, most are dual-fuel and still rely heavily on conventional fuels. Clear demand signals, such as long-term offtake agreements with defined prices and volumes, are essential to give fuel producers the confidence to invest. For producers, the upfront capital expenditure for new plants and distribution networks is high, and the return on investment depends on a market that has yet to fully materialize. Without these commitments, projects will remain risky, and the transition will continue to stall.
In the container segment, ship owners are forming strategic partnership to secure low-GHG methanol and accelerate market development. These long-term agreements connect fuel producers, energy suppliers, and ports to guarantee volumes, stabilize pricing, and anchor new production capacity. These commitments reduce investment risk for producers and ensure ship owners access to low-GHG methanol at key hubs. By coordinating production, certification, logistics, and bunkering, these partnerships create integrated value chains that support the growing methanol-capable fleet and send strong demand signals that help unlock new projects and scale supply. Methanol offers a practical pathway to lower carbon shipping, but scaling requires bold commitments across the value chain. Through collaboration and clear demand, low-GHG methanol can be scaled globally, bringing the industry closer to net zero.